Hello everyone. Today we're going to be starting the chapter forces and let's start. So first we're going to talk about force. Force is a push or pull. This is something that we use in our everyday lives whenever we are like pushing a shopping cart or pulling on a door. We use the word push and pull. This signifies force because we're pushing or pulling on the door. We're forcing the door. The SI unit of force is newtons. So this is very important and it's a vector quantity, so it has a direction. The next thing that we have is very important is the formula for force. So just like we use formulas to calculate the velocity, speed or time, we can use formula to calculate force. The formula for force is F is equals to m multiplied by a, where m is the mass and a is the acceleration. So for example, a person slaps a door. The mass of his hand is, for example, 2 kilograms, and the acceleration of his hand while he slaps the door is 2 meters per second squared. So the force exerted is going to be F is equals to 2 multiplied by 2, F is equals to 4 newtons. The formula is very important and it's going to help you a lot during all your calculations. Moving on, force can cause a moving object to slow down or speed up. So what this means is that if there's an object which is at rest, a force can cause it to speed up, or if there's an object which is already moving or speeding up, a new force can cause it to slow down. A force can make a stationary object move. So every kind of movement, speeding up, slowing down, or starting a motion is caused by force. Let's talk about gravitational force, which we call weight in our slang. So gravitational force is a force which acts upon all the objects on a planetary body, in our case, which is Earth. So everyone on Earth experiences gravitational force. The force caused by the gravitational field of the Earth is the gravitational force, and it is a pull force. Pull force. Now, why do I say that? It's because, for example, this is Earth, and this is a box. Now the earth pulls the box towards itself. So this is a pull force. If the earth pushed the box away, it would have been a push force. Like for example, two magnets. As the poles are same, the two magnets are going to push each other away. So this is a push force. The next force that we have is air resistance or drag. So the force experienced while traveling in a fluid is something like air or water, and the force that we experience when while moving through a fluid is called air resistance, and it is always opposite to the motion. So in if we're traveling in a fluid, guys, just remember that fluid is like, for example, air around us or water or any kind of liquid. This is a fluid. So if we're, for example, traveling in the air, whichever direction that we go or move in the air, we're going to experience a force opposite to that. So for example, if this is ground and there's a ball moving towards the right, it's going to experience a force towards the left. This force will be our air resistance. If there's a ball moving downwards, it's going to experience a force upwards. This force is also air resistance. The size of air resistance, like how big the force is going to be, depends upon how fast the object is moving, and we're going to talk more about this while we do some examples later on. Moving on, the next force that we have is tension. Tension is the force that is exerted by some kind of rope, cable, or chain. So in this case, we have the struck, which is holding on to this ball. Now, the struck is holding on to this ball through this cable right here. Now, if we look at the ball, we see that there's weight acting on this ball. There must be some kind of force which is exerted in the opposite direction to the weight, which helps the ball stay in equilibrium. Equilibrium means to stay in its place, because if weight was the only thing acting on the ball, it was going to fall down. But there's something holding on to the ball and making sure it remains in its place. This force is comes from this cable right here. This is the tension force. Another force we have is electrostatic force. Electrostatic force is the force between charges. So, like positive and positive charge in this example repel each other. The push force between these two like charges is electrostatic force. The attractive force between two opposite charges is the pull force and is also called the electrostatic force. Magnetic force is the same. If we have two magnets, the like poles will repel each other. This is the magnetic force, and the opposite poles will attract each other. Another force we have is the driving force or thrust force. So, if we are moving in a car, or for example, if we're in a plane in this example, we can see that there's gravity, weight acting on the plane, there is air resistance acting on the plane, and there's something which goes opposite to the air resistance, which helps the plane move forward in this direction. This force is called thrust or driving force, and this force is caused by the engine of the object. So, for example, in this case, there's an engine in the airplane which is helping it to move forward, and this force is called thrust. Now, let's focus on a free body diagram. A free body diagram is a diagram that we use to show all the forces acting on an object. So, for example, in this diagram, we see a box. Now, we have four forces acting on this box. One of them is weight, and we can see that weight acts downwards due to the gravity. Then we have a normal force. This normal force is exerted by the surface to cancel out weight, because if weight was the only thing acting on the box would break the surface and fall down. Next, you have applied force, which is a force, maybe a person is pushing the block towards the right. This is the applied force. And then we have friction force, which is going against the applied force. This is going to be in the opposite direction. Friction force, just like the air resistance and drag, works opposite to the motion. So, for example, if the force is acting towards the right, the friction will always act opposite to the force. It will act towards the left, just like we see in this example. So, the box is being pushed, which is the first force. The box experiences friction. This is the second force. The box experiences weight, which is the third force, and then we've got the normal force. So a normal force is a force caused due to weight. It balances out weight so the object doesn't go crashing down. Okay, so we have another diagram here. We see that there's a box and there's two boys pushing the box from the right and the left. So the boy on the left pushes the box with a force of 15 newtons and the boy on the right also pushes the box with a force of 10 newtons. But as we see that the boy 1 is pushing the box towards the right and the boy 2 is pushing the box towards the left. So both the forces are going in opposite direction. Now, if we see the magnitude of the forces, the force for boy 1 is 15 newtons while the force for boy 2 is 10 newtons. As we know 15 newtons is bigger and 10 newtons is smaller, we can assume that the box moves towards the right. But how do we prove this mathematically? So the first thing that we need to do is take one side to become positive. So in this example, we're going to say that any measurement towards the right side will be considered positive, and to the opposite of that is obviously going to be negative. So this means that boy 1, the force exerted by boy 1 is going to be positive 15 newtons, and the force exerted by boy 2 is going to be negative 10 newtons. So we're just going to add both these forces as we did here. So positive 15 newtons plus negative 10 newtons is going to become minus 10. So minus 10 newtons, and the resultant force that we get is 5 newtons towards the right. Now how do we know that it's going to be towards the right? It's because it's positive, and we just stated that right side is going to be positive. So by the sign of the resultant force, we can see that the resultant force acts towards the right. We also need to make sure that we understand that usually the length of the arrows indicate how big a force is. So for example, if there's this white box here and there are two forces, one of them is going to be this and the other is this, we can see that the upper arrow is much bigger than the lower arrow, and this indicates that the size of the force for the upper arrow is going to be larger than the lower arrow. Okay, let's talk about some laws, Newton laws. So the first Newton law states that an object remains at rest or continues moving in a straight line at a constant speed until acted by on a resultant force. Now this definition is very long and it can be a little bit scary, but it just means a very simple thing. This definition means that an object is going to continue its state of motion unless acted on by a force from outside. So, for example, if there's a ball and it's at rest, it is going to stay at rest until a force acts on it. This is very logical, and we see like nothing moves until we push it or pull it. So, the law is talking about the same thing, that if there is something at the state of rest, it's going to remain at the state of rest unless or until a push or pull force from the outside comes and acts on it. Another thing that it states is that if there is something which is moving at a constant speed, it will remain moving at a constant speed until something acts on it and stops it or slows it down or makes it change directions. So, for example, if we throw a ball, the ball only stops because friction acts on it. So, for example, if we threw a ball in space, the ball would continue moving forever until some other kind of force came and stopped it. This proves Newton's first law. So, to put it in simple terms, Newton's first law just states that an object is going to remain in its state of motion unless acted by some other external force. This is something that I've explained in text here, as we can see. This is very detailed, and I'm going to be sending you guys the notes so you can check it for yourself and uh, look in detail if there's something that confuses you. Uh, okay, so the next thing that we're going to be doing is how force affects velocity. So by Newton's first law, we learned that an object continues its state of motion, meaning that it will remain in rest or in motion with a constant speed unless an external force acts on it. So now we're going to see how force changes the velocity of an object. So here we have a ball. The ball is moving with a speed of 10 meters per second on a surface without friction. So we know that the ball is going to continue this speed or velocity forever. But what if we push it with a 10 Newton force? Now we see that once we push it with a 10 Newton force here, the speed increases to 20 meters per second. So this is because force basically causes acceleration or deceleration depending on its direction. So whenever there is a net force on an object, it's going to accelerate or decelerate that object. So if this is a ball and we see that there are two forces, one from the right, another from the left, and if we take out the net force and we see that maybe the force on the left was a bit bigger, so there's a small red net force acting on this object is going to accelerate. Now, what does acceleration mean? It means that its velocity is going to change. Depending on the force, the rate of change, the acceleration is going to be different. So, in this example, we just take it on its face value. So, by 10 Newton push, it increases by 20 meters per second, for example. The point of this diagram is to show that force causes a change in velocity. The net force was 10 newtons, so the ball experiences a push of 10 newtons, so its velocity increases. Now, in this other diagram, we see that a ball is moving without friction. The same ball is moving without friction with the same speed. This time, we push the ball with a force of 20 newtons, but in the direction opposite to its motion. So, the ball was originally moving towards this side, but we pushed it towards the left with a force of 20 newtons. When we push it towards the left with a force of 20 newtons, we see that in the end, our ball starts moving towards the left with the speed of 10 meters per second. So the force and its direction completely changed the motion of the ball. This time it experiences a force of 20 newtons from the opposite direction to the motion. So the ball changes its direction of motion. The magnitude remains 10 but in the opposite direction. So now we're going to talk about resultant forces. So this box here, it has three forces acting on it. So there are two forces from the left and one force on the right. And when we, so okay, so let's do this one. So we take right side as positive. If we take right side as positive, we can calculate the net force. This means that 2 plus 5. Now, why are these two positive? Because they're moving towards the right. These two forces are towards the right, so they're positive. -1. And the 1 is negative because it is on the opposite direction, is equal to 6. Now, keep this in mind that this 6 is positive. This is positive, which indicates that this force is acting towards the right. So when we draw the diagram, we can see that the 6 Newton force acts towards the right. So the basic formula is add forces in the same direction and subtract the ones in the opposite direction. The same calculation is done below, and we can see that the answer is indeed 6 newtons to the right. Now let's talk about Newton's second law. Newton's second law basically states that force is equals to mass of an object multiplied by its acceleration. This is the formula that we talked about in the beginning of the video, and this is one of the Newton's law. This is the second law of Newton, and this is the formula we use to calculate forces every day in our lives. Uh, so this is very important formula, and it's going to help you in a lot of your problems. So it's best that you memorize it and learn how to use it efficiently. So in this example, we see that a man with a mass of 70 kilograms uh, experiences. Oh, okay, sorry. Okay, so in this example, they're asking us to calculate the force on a man with the weight 70 kilograms. So we've got our formula here. We know that the mass of the man is 70, and we also know that the acceleration due to gravity on anything is 9.81 meters per second squared. So we just put these values in our formula, and we get that the weight of the man is 686.7 newtons, or we can write it as 690 newtons. The next question says a cart is pushed with a force of 30 newtons. It has a mass of 1500 grams. Calculate its acceleration. So let's see what we have. We have the force, tick, and we also have the mass. But the mass is in grams, so we must convert it to kilograms, the SI unit first. This is very important, and if you don't convert it, you're going to lose your marks because the answer is going to be incorrect. So we convert it to 1.5 kilograms. Now we write the formula and we just put in the values that we know. So force is 30, done. Mass is 1.5, this is also done. And we need to calculate acceleration. We just solve for A and we can see that the answer is 20 meters per second squared. The last law that we're going to be talking about is Newton's third law. The Newton's third law states that when an object A exerts a force on an object B, then the object B exerts an equal and opposite force on object A. Okay, so in this diagram, we can see that the pairs. So in this diagram, we see a book which is just resting on a table, and we see that the book pushes the table downwards like this. Now, because of Newton's third law, we know that the table must also be pushing the book upwards. So the table also pushes the book upwards, and this is one pair. And then we see that there is gravitational pull on the book from the earth. So if this is the earth and this is the book, the earth is pulling the book downwards. But due to gravitational Newton's third law, we also know that there must exist another force in this pair. So that force is going to be the pull of the book on the earth. So the book also pulls the earth with an equal magnitude in the opposite direction, which means towards the book. Now, one thing that you guys must remember is that a pair of these Newton's third law forces don't act on the same object. So, for example, if this is the book, it has the normal force and it has weight. These two cannot be the Newton third law pair. Why? Because they're acting on the same object. The pair of forces in the Newton's third law must act on two different objects. So, the earth and the book example, one of them is the pull of the book on the earth, so upwards, and the other is the pull of earth on the book, so downwards. Now, this force acts on the book while this one acts on the earth. And in the table example, we can see that if this is the table and this is the book, the push of book is on the table, and the push of table towards the book is on the book. So these two forces act on different objects. I hope you understand, and if you have any questions, you can ask me in the comment section. Thank you for watching.